All right, this is Mr. Smith here, Algebra 2, Section 7.6, Part 2. We are working on solving equations. What we saw in the last time was we were solving exponential equations. The way that we would bring the variable out of the exponent is by taking a logarithm on both sides. In the second half of this section, we're going to work on solving logarithmic equations. To solve logarithmic equations, we're going to use this idea that the textbook calls exponentiating. And what they mean by that is we're going to be given an equation. We're actually going to use that equation and we're going to shift that up into the exponent's place, and we're going to add in a new base. And textbooks call this process exponentiating, and this is going to be the idea for how we proceed for the rest of this section. Generally, I'd say this is the culmination of Chapter 7. This is what we've been working towards, is the ability to solve these equations. Okay. Now, we start off here with an easier problem. It's easier in the sense that, look, if I know that log base 5 of something equals log base 5 of something else, then the only way that's possible, the only way that can happen, is if the two arguments, 4x minus 7 equals x plus 5. For instance, if I know that I have ln of 4 equals ln of x plus 1, the only way those two things are equal is if x plus 1 also equals 4. Right? If x was 5 here, well, ln of 6 doesn't equal ln of 4. That doesn't make sense. Okay, so the same idea applies over here on this problem. Look, the only way this could actually work is if 4x minus 7 equals x plus 5. That's it. That's the only possibility here. So that's a linear equation. We solve it, and x equals 4. Right, subtract the x, add the 7, divide by the 3. You should get x equals 4. Okay. All right. By and large, this is not the type of problem we're going to be working on. It's, again, helping us get to where we want to go. This is the problem type that we want to spend our energy on. And we can't use that cute little trick I just pulled on the last problem. Right, because I don't have logarithms on both sides. So what the idea is we're going to exponentiate this problem. Right? So I have an equation, and we're going to shift this equation up into the exponent's place, and I'm going to introduce a new base. And the new base in this case is going to be 4. Okay. So I'm going to introduce a 4, and now I'm going to put 4 to this power, and that's going to equal 4 to this power. Okay, so we're shifting the original equation up into the exponent's place, and we're going to get 4 to log base 4 of 5x minus 1. And we're going to get 4, that equals 4 to the third power. Okay, so what I'm doing is I'm shifting the original equation up into the exponent's place, and I'm putting a new base of 4 in. So 4 to this log base 4 of 5x minus 1 equals 4 to the third power. But why did I choose 4? And the answer is because I want to mimic, or I want whatever this base is here to be my new base. And the reason is because 4 to the power log base 4 just cancels out. And so we're left with 5x minus 1 equals 4 to the third power. And that is a linear equation. Okay, look what happened. I have 4 to the log base 4 of 5x minus 1, but 4 to the log base 4 drops out, leaves me 5x minus 1, and now we solve this. So 5x equals 65, x equals 13. And we're done. And we're done. Okay, let's see this again. All right, so here we go. Same type of problem. I want to undo the logarithm on the left side. I want to get rid of that logarithm. So to get rid of it, I'm going to exponentiate it. I'm actually going to shift it up into the exponent's place. And I'm going to introduce a new log, I'm going to introduce a new base, and that base is 5. So we're going to create a new equation with 5 as the base, and now this piece will be the exponent on the left side. Log base 5, 3x minus 8. And this piece will be the new exponent on the right side. But of course, 5 to the power of log base 5, that cancels out, and just leaves us 3x minus 8 equals 25. The fact that 5 to the power of log base 5 cancels, that was the whole goal. That's why we were doing what we were doing. Again, this is just linear. We solve this, and x equals 11. So we can take this approach and even go back to the original problem that we looked at, right? If we look at this guy, and some of you may not have liked the idea that I just disregarded the logs. Smith, wait a second. You totally just ignored the fact that there were logarithms there. And that's true, I did. However, if I were to exponentiate this and introduce a base of 5, look what happens. Right? This is 5 to the power log base 5, and this is equal to 5 to the power of log base 5. Well, what happens on both sides? Yeah, the logs just cancel out on both sides, and it really does just leave me 4x minus 7 equaling x plus 5. Okay. Now, on this problem, you don't have to think of it that way, but if you did, it still works out. Okay. So let me pause here. Are there any questions on what we're doing or what the objective is? Okay. See, none. Let's complicate the process now. So now we have 2 logarithms on one side. And I don't want to have 2 logarithms on one side. I want only 1 logarithm on one side. Now I could try to shift the logarithm over to the other side, but I promise that doesn't make our lives any easier. Because now I have a number plus or minus a logarithm on one side. So what I ideally want, what I really want here is just 1 logarithm on one side. How can I do that? How can I do that? So the question is, how can we combine this log 5x, and by the way, remember the base is just 10. Yeah, the base is just 10 here. How do I combine this common log of 5x and this common log of x minus 1? And the answer lies in section 7.5. We have 4 properties. And one of them tells me that I can combine these as 1 logarithm through the process of multiplication. So now we need to employ our properties. And now it's okay if I exponentiate this. I'm going to take this equation, I'm going to shift it up into the exponent's place. And this is going to be 10 to the power, common log, or log base 10, of 5x squared minus 5x. And it's going to equal 10 squared. But of course, 10 to the power log base 10, that cancels out. This piece cancels out, and it just leaves me 5x squared minus 5x equals 100. And this piece now comes down onto the ground floor, and it creates what? What are we looking at there? That's a quadratic equation. How do I solve quadratic equations? Set them equal to 0. And we can use factoring. We can use the quadratic formula. Although before we do any of that, I see that all three of these numbers will divide by, all of them divide by 5, so let's make our lives a little easier. So that looks a little nicer, I think. And it factors into x minus 5, x plus 4 equals 0. So x equals 5, and x equals negative 4. Yes. Those are our answers. No, they're not. We got to check for extraneous solutions now. But I'll tell you, the process of checking for extraneous solutions isn't so bad. What's the domain of our logarithmic function? What values am I allowed to plug in for the argument? Now, we should know this. When we talked about graphing logarithms, we talked about how they look and what domain values and what values I'm allowed to plug in. For instance, right here, the argument of a logarithm, that's this piece, has to be greater than 0. Let me say it again, and you need to make sure you take note of it. The argument of a logarithm has to be greater than 0. What that means is if I plug in x equals negative 4, that's going to make this negative 20. That's not greater than 0. That solution's extraneous. That solution's extraneous. If you plug in the other one, since this is common log, anyone can plug this into any calculator. And if you plug in 5, you get log of 25 plus log of 4. And if you punch that in, it does indeed equal 2. Okay? All right, so let's go back through the whole process and see how this thing flows. Step 1, we need to combine our logarithms to one logarithm. We use our properties to allow us to do that. Step 2, we exponentiate. We bring the new equation up into the exponents, and we add in a base of 10 on both sides. Notice this does not say 2 to the 10th power. I promise you a lot of mistakes will be made right here because you'll write 2 to the 10th power instead of 10 squared. Very careful there. Okay. Now on the left side we get things canceling and we're just left with 5x squared minus 5x equals 100. But this is a quadratic equation. So we solve it like a quadratic equation, but we must be careful in the last step about extraneous solutions. And that gets us there. That gets us there. Okay? So here are 4 problems. For those of you in class and for those of you watching the video, I'd like you to pause the video now, and I'd like you to work on all 4 of these problems. Okay? So please pause the video now. Get to work. All right. Welcome back. So I went ahead and just did the first 2 there. On the first one, we can just equate 7x minus 13, 2x plus 17. Because they're both inside of a logarithm, we can essentially disregard the fact that there's a logarithm there. Otherwise, if you want to exponentiate it and take e as your base, so e to the ln equals e to the ln, you can think of it that way as well. On 6, I went ahead and exponentiated this with, so shifted these guys up into the exponents place, and I get 3 to the log base 3 of 2x plus 9 equals 3 cubed. All right. So on the left side, our logarithm cancels out with our raising something to a power, so we get 2x plus 9 equals 27, x equals 9. On number 7, we're going to do a similar process. So here we'll create a new equation where 4 is the base. We get log 4 of 10x plus 624 equals 4 to the 5th power. So this new equation then becomes 10x plus 624 equals 1024. Okay, that's linear. So we should get one solution, and the solution is 48. 40. X equals 40. Okay. The last problem, that's the meat of this section. This is going to be a harder one. So the first thing we want to do is we want to apply our properties. So our properties say I can combine these 2 logarithms as 1, so this is log base 6 of x times x minus 9, and that just equals 2. And now I'm going to exponentiate this, and so the base is now going to become 6, so this would be 6 log base 6 of x squared minus 9x equals 6 squared. So this is going to be a quadratic equation, x squared minus 9x equals 36. We can bring over the 36, this thing will factor into x minus 12, x plus 3, which means x equals 12, and x equals negative 3. Except I know that this original problem was logarithmic, and the argument of a logarithm has to be greater than 0, and if I plug in negative 3, that's not going to happen. So that tells me that this is not our solution, and this, if I plug in 12, it does indeed work. Okay. So, section 7.6 is all about solving equations. The first half of it is about solving exponential equations. The second half is about solving logarithmic equations. This is really what we've been aiming towards this entire chapter. Thanks for your attention. Good luck in your homework tonight. This is Mr. Smith signing off.